Hey everyone, how's it going? It's Liz from the Dfinity Foundation, and welcome to Community Conversations. This is an opportunity for you, the community, to hear from contributors within the internet computer ecosystem, as well as ask them questions live. So today we have Principal Software Engineer Ulan Degenbayev and Senior Researcher Helga Baumann, who will go over the current NNS motion proposal regarding canister sandboxing. Essentially, this is to ensure that when there are malicious canisters running on a subnet, that other canisters within the same subnet are not impacted. So I'm going to turn it over to the two guys I just mentioned. Thanks very much.
Thank you, Liz. Right, so today Helga and I will give more details about the canister sandboxing proposal. There is the corresponding NNS motion was submitted yesterday, and you can find it under the ID 2699 and 9. So it's currently voting is ongoing there. So the agenda for today is first we will give some background and show how internet computer runs WebAssembly code. Then we are going to define the problem we are trying to solve, and then describe the proposed solution, which is the process sandboxing, and conclude with discussion of the trade-off space and technical challenges in the implementation. All right, so we are going to focus on the execution layer of the internet computer. This layer is responsible for running WebAssembly code of smart contracts. And you can think of a smart contract as a collection or combination of WebAssembly code, WebAssembly memory, stable memory, and the system state, which contains other information related to the canister. One important distinction between memories and the system state is that a smart contract has unrestricted access to both WebAssembly and stable memory, in the sense that it can read and write the memory in an arbitrary way as it likes. And in contrast to that, the system state is protected. So not all modifications are allowed, and only certain modifications that follow the rules of the specific field in the system state are allowed. Yeah, so this distinction will become, you will see it later on in the talk. And from now on, I'm going to refer to smart contracts as canisters because it's shorter. So now if you take one subnet, it consists of many canisters. And if you take one replica and look inside this replica process of that subnet, there will be execution layer that is running all these canisters. And running a canister means we get a message from the messaging layer, and then we find the corresponding canister. Within that canister, we find the method or handler of that message, and then we execute the method inside the WebAssembly engine. As a result, we get the new state of the canister together with the other messages. And the important piece here is that we have a process, and within this process, there are many canisters running, right? And now Helga will tell us about the security implications of this setup.
Yeah, thanks, Ulan. So if we look at what Wasm execution actually means in
Helga,
the context...
I think you are muted.
I should not be muted. 1 second.
Oh, I can hear you, Helga. You're not muted.
Okay, good. Sorry. Good. Let's take a look at how the execution of the Wasm actually happens inside the replica. The way it looks like is that the organization of the replica as a process looks a bit simplified as follows on this slide here. So inside the process address space, we have on the one hand the replica code and the replica data. So this is all the private data that the replica needs to maintain. This also includes, for example, secret keys and other things that the replica needs to operate. Part of this replica code is actually also the system API that is available to canisters to interact with the IC. And then in order to have canisters running, the canisters, the canister memory has its Wasm address space modeled simply as a small section of the larger replica process address space. And the canister code the WebAssembly code is translated into native code that will be directly executed by the CPU. And so this is from the operating system and CPU point of view, all in a single process address space. So yeah, on the next slide, let's have a look at what the interactions are that we want to have and not. Of course, we want the native code for the WebAssembly to be able to access the Wasm address space. That is what it needs to operate. And we also want it to allow it to make selected calls into the system API, into the well-defined entry points that we have for this. But the interactions that need to be absolutely forbidden is, of course, any other access to replica data or data of other canisters, obviously, and also any execution of other code besides the system API inside this process. What the interesting question now is, what is the actual barrier preventing this kind of access? And on the next slide, I'm trying to summarize this, and the gist of it is that it hinges on the correct generation of the native code from the WebAssembly code. The code that is generated has a very particular structure, and this needs to be very carefully crafted in order to prevent the kind of accesses that need to be forbidden. This also implies that there are actually a number of checks in the generated code, and with this, there's a little bit of a goal conflict there, because from a compiler perspective, of course, you want to make the execution as efficient as possible, so you want to optimize out as many checks as possible to not waste CPU cycles. On the other hand, if by some kind of mistake you optimize out one check too many, then this might actually cause any kind of a gap and might cause a forbidden access. And as we've observed from many other similar systems, VM systems, any single access into forbidden area very quickly escalates into a complete compromise and complete control of the host process. So this is the thing to keep in mind, and it hinges really on the correctness of the compiler, of the JIT compiler. And a single flaw in there may compromise the entirety of the system. We know that many other JIT compilers have been compromised. There have also been flaws in Wasm time. We don't think we shipped any flawed version yet, but it is still to be noted that we need to be aware of this potential problem. There's a second problem, and the second problem is even if we assume that the compiler is 100% correct and always generates correct code, to the CPU, the entirety of the process address space is really just a single flat address space, and to the CPU, there's no distinction between any of the replica data or canister data or replica code or canister code for that matter. To the CPU, it's all the same. That means while the CPU is executing either, it will very happily speculate any kind of access into any of the addresses within the larger address space of the process. And that means that it is in principle always susceptible to kind of speculation attacks, and by such speculation attacks under certain circumstances, I won't go into too much detail here, it is possible to exfiltrate data using this, and exfiltrate data that is nominally inaccessible. And this is even if the compiler is working 100% correct. It is theoretically possible to produce Spectre-resistant code. There have also been attempts to do that, unfortunately not with so great access, and the consensus actually in the security field is that it is kind of a lost cause, and that is generally cheaper to just bite the bullet and say, okay, well, the CPU is only going to protect things that are in distinct address spaces, but we will not try to stop it speculating within the same process address space. It's extremely expensive and extremely difficult and brittle to do. So to both of these kinds of attacks, process sandboxing is of course the suitable defense, and the model that we want to use is that each canister runs in a dedicated process, and that we move the enforcement of access restrictions that we have on the canister to the process level. That means even if the process is behaving in arbitrary ways, it cannot do more than we want the canister to be able to do. So we didn't really invent sandboxing, but it's pervasive. So many projects do this, and we are of course looking also into how precisely they are accomplishing that. There are techniques known to us that we're also investigating and studying for use in there. So this is actually kind of our main inspirations: Chrome Sandbox and Android Sandbox. That we'd also like to model this after. So the thing that we actually need to isolate is actually multiple directions. If we look at the sandbox process, there's on the one hand the communication to the replica process, which is the controller and the main logic of the internet computer. But the other interfaces, of course, we need to ensure that the sandbox processes cannot communicate sideways to other sandbox processes or interfere with them in any way. And thirdly, the sandbox process can, in principle, also talk to the operating system kernel. They need to communicate with the operating system kernel in some way. Otherwise, they can't do anything. And of course, also this interface we want to guard closely to prevent anything that goes wrong in the sandbox from being used to escalate further by attacking the operating system kernel or other components in the system. So what do we want to first of all, how can we achieve the isolation, and then what do we want to protect with this isolation? So on the next slide, I have given a rough breakdown of possible approaches to the sandboxing, and we can roughly distinguish between two approaches in terms of who initiates the isolation. We can have discretionary process isolation. This means that the sandbox process kind of starts up unconfined with no isolation yet applied to the process, performs some preparation, and then drops privileges into a mode where it then operates confined and subject to sandboxing restrictions. The other approach is to not let the process itself do that, but enforce this mandatorily directly from the operating system. That means the process cannot even enter any preparatory stage. It will immediately be dropped into the isolated mode, and the operating system enforces this across the entire lifetime of the process. And the enforcement front, how the isolation is enforced, there's also kind of different techniques that's used in a different context, discretionary and filter-based. This basically entails that the sandbox process describes what operations should be allowed, basically describes what privileges should be retained or what privileges should be dropped, and hands this description over to the operating system, and then expects the operating system to act on this description given voluntarily by the sandbox process during its startup phase. The other option is to have, again, mandatory enforcement such that the sandbox process does not have the capability or the need to express any of its confinement requirements, but it's enforced and hard-coded into the entire system, and the operating system also enforces this independent of the sandbox process doing anything. What we would prefer is mandatory isolation as much as possible, and this is also quite feasible for a project like the IC, where we control and can shape the entire software stack around the requirements of isolation. This has a number of benefits, particularly all of these voluntary mechanisms have the potential of exposing quite a complex kernel interface to process that itself might actually be prone to abuse. And so preferentially is for mandatory enforcement rather than discretionary. So what we assume basically is that a successful attacker may take complete control over a sandbox process. And what we particularly assume is that such an attack is basically only possible by the canister owner. The thinking here is the following, that any such attack requires specifically crafted WebAssembly code to confuse the compiler or confuse the runtime in suitable ways. So really only the canister owner providing the code for the canister will be able to conduct this. So we do not assume a threat model that you have an arbitrary and canister without malicious intent. This is attacked by an outside attacker without the canister owner's consent. We do not think that this is possible. So in this scenario, in this threat scenario, we basically assume that the attacker equals the canister owner. And what a successful attacker, provided that he can, for example, confuse the WebAssembly compiler, may accomplish is that they can read and write arbitrary memory addresses in the sandbox, that they may actually gain arbitrary code execution within the sandbox process. And of course, they can also talk to the replica and imitate the actions that a legit canister could also do. And what we want, the protection that we want to accomplish under this scenario is that we want to guarantee integrity and confidentiality of the other portions of the IC. So this is depicted on the next slide again. What we in particular want to guarantee is integrity and confidentiality of all other canisters besides the one that is used as the attack vector. And that we also want to guarantee integrity and confidentiality of all IC metadata. So this is, for example, the private keys of the IC, but this is also input queues, incoming queries, possibly distinct for other canisters, artifact pool, and so forth. All of the internal data structures required for IC operations are, of course, also protected. And what we also want to protect is the integrity of the metadata of the attacked canister. So this is basically the system state, all of those that cannot be directly manipulated by the canister normally. And this includes things like, for example, cycles balance or token balances in general. So even if the attacker takes complete control over a canister sandbox, we want these protected still, and that they cannot be manipulated arbitrarily, but still only within the limits of what would be allowed to the canister owner. One thing that we may not be able to guarantee is that an attacker might actually still cause a bit of disruption to the subnet, and that is the following problem. When a canister sandbox has been taken over completely by an attacker, they may actually cause the canister on a particular replica instance to behave erratically, and particularly it may break the determinism assumption that we normally have on all canisters. So normally all canisters on all replicas in a subnet execute in lockstep. They will deterministically produce the same result, but it is possible to break this determinism. The effect of that is that, of course, the node instance to which such an attack has been applied will diverge as far as this canister goes, at least from the other nodes. That itself is actually not a problem. Basically, the protocol will detect that. It will detect that this node is faulty and actually force it into state sync, and it will take over. But hypothetically, it might be possible for an attacker to attack a sufficient number of nodes in the same subnet using the same technique, such that actually this state sync is not immediately able to take over. And this might indeed stall a subnet. So, and this is something that we cannot entirely prevent using the sandbox mechanism. It could be prevented actually using higher level mechanisms that detect that the divergence is caused by a single canister, and then possibly take immediate corrective action to, for example, confine the offending canister, but let the subnet otherwise continue. There are ways to do that. However, this is one step beyond what we are doing with Sandbox, and for the initial version, we will still have this that it requires corrective action by the NNS under such a scenario to get the subnet working again. It's not clear whether this is a very severe attack, because it requires lots of effort by an attacker taken to actually relatively modest gains, namely temporarily stalling a subnet, and but after corrective action is taken, this would also be rectified. So it's not even clear how we're not in full agreement how much of a threat this actually is. So with that said, I'd like to hand back to Ulan to discuss more about the implementation and complexity and trade-offs that are there. Thank you.
Thank you. Right, and to give you some idea on what we are going to gain and lose with sandboxing, so here's a trade-off space, and we are taking the current version as a baseline, and it is shown in white, and it is in the middle of each dimension. And now the blue circles show like how these dimensions we expect, or our estimate for how these dimensions will change with sandboxing. So to the right it's better, to the left it's worse. And for security, we think like it's going to be a huge improvement for security, because like combined with the existing WebAssembly engine sandbox, the process sandbox will give us like maximum security that's practically achievable for running untrusted code. And we are going to pay for that with increased complexity. So the code complexity is going to increase because the existing code assumes that everything is running in a single process, and we will have to change that assumption and like support multiple processes, manage these processes, and manage the state within processes. So the complexity is going to increase, but we think it will be manageable. Now, regarding the performance and memory, like there are question marks, because like we will know this for sure only after implementing and actually measuring. But our initial estimate for performance is that we expect that it's going to improve, and that may sound counterintuitive because processes have higher overhead compared to threads. So we are going to lose performance in some areas, but there will be also areas where we will gain performance. And one example of such area is performance of system calls. So currently some system calls are bottlenecked on the kernel level, where the kernel has locks and semaphores set up a process. And we are hoping that when we move canisters to different processes, we are going to avoid this per process bottlenecks, and we will see performance gains. Like how it's going to balance out in the end, like it's unknown, but our intuition is that performance in the long term will improve. It could be the case that the initial version will have like performance on par or maybe degrade because it will not be as optimized, but long term we expect performance gains here. Regarding the memory, we expect that memory usage will increase because there is a process overhead. Having said that, we expect to do some improvements in the internal data structures to support sandboxing. Like one example is page allocator, like allocator for WebAssembly modified pages. And so if we implement our own page allocator, it will be tailored for our use case, and the fragmentation of the page allocator will be much lower compared to the built-in Rust allocator. So here again, like in some cases, like memory is going to increase, but we also will do optimizations to reduce memory usage, and like how it balances out needs to be measured in the future. And if we sum up everything, like I think, like in my personal opinion, like the sandboxing is definitely worthwhile, and the benefits outweigh the disadvantages. Yeah. Now I'm going to go through the technical challenges that we expect and that needs to be solved before we can ship sandboxing. The very first one is engineering challenge, how to retrofit multiprocessing into the existing code that assumes that everything is running in a single process. And the good news here is that Helge already implemented a prototype, and that prototype is currently running and it passes all tests. The only issue with the prototype is the performance. It's currently at least 2 times slower than the baseline. And we have ideas on how to fix performance. And for that, we need 2 optimizations. Like the first optimization is improve memory management. So the replica process is a source of truth for canister state and memory. So this means like memory and canister state are managed by replica. And this means that in order to run the canister, we would need to somehow transfer memory pages over to the sandbox. Then sandbox runs the canister and then sends back the modified pages to the replica, and then replica can commit those pages. And this is how the prototype implements it. And it is suboptimal in the sense that there are many pages being copied back and forth. And what we want to do instead is to implement shared memory so that both replica and sandbox process can access memory directly and thus avoid copying a lot of data. Another source of slowness is handling of the system API. As I said, the system state is stored in the replica, and it needs to be protected from the sandbox, so to not allow arbitrary modifications. And currently, what prototype does is, for each system API call, it does inter-process communication to call the replica and then gets a result. So this causes a lot of ping pong between the two processes. And what we want to do, the idea is to actually have a copy of the system state on the sandbox side so that all system APIs can be resolved locally. And after the execution, sandbox gets all the changes or delta to the system state and sends it to the replica. Replica can then verify that all these changes are actually valid and according to the rules. And once they're valid, it commits those changes. Right. And our hope is that if we implement these two optimizations, which are by themselves large projects, that the performance issue will be fixed and sandbox will be in this state or shape ready for production. Yeah, that brings us to the end. And let me conclude by summarizing what we already said. So the process sandboxing is a standard technique. It's used in industry by many applications to securely run untrusted code. Together with WebAssembly engine sandbox that already exists, process sandboxing will give us maximum security. We have to pay for it with increased code complexity and engineering time. And yeah, I also put here the links to the NNS motion and to the discussion forum thread where you can find more details. And yeah, that's it. Thanks for the attention. And I think we can switch to questions and answers.
Cool. Thank you so much to both Ulan and Helga. So I think maybe we can just go back in. We just got a question from Jordan saying, why are you guys so awesome? Maybe Ulan can take that one. Okay, so I'm just going back through the chat to see what sort of questions we got. The first question was around a previous slide of yours, Helga. I'm just clarifying that the process is an OS level process, and community members in the chat confirmed that. So next question, does this mean that currently multiple canisters run in the same OS process, hence having access to each other's memories? And could this be accessed with a low-level language like C that has unbounded memory access?
Okay, yeah, maybe I can answer that. So the first part is correct, that they are running in the same process. The second part, they can access each other's memory, is actually not correct. Or this is only correct if they are able to find a bug, for example, in the Wasm compiler that generates the native code. So this is still there as a barrier. You cannot just write and access a random memory and access other canisters' memory unless you really find a flaw there. With low-level languages, well, I mean, you can also write WebAssembly code in low-level languages, but even the resulting WebAssembly code is still subject to WebAssembly restrictions, and you will not be able to gain access to canisters just purely by writing in low-level languages, or maybe just writing WebAssembly directly. This will not work.
Mm-hmm. Great, thank you. So next question, do you aim for POSIX compatibility or Linux exclusively? If the latter, would it be possible to have per-thread memory protection, Wasm compiled code and heap allowed, and do thread switches for system interface calls?
Okay, yeah, I think that this goes to system integration part, so I think I'll answer that too. This will be Linux only. POSIX does not allow actually very fine-grained access or sufficiently fine-grained access control to do any kind of such isolation. So under POSIX rules, for example, if you have two processes running under the same UID, they can do whatever to each other, and there's no limit. You can also practically see those processes. So this goes far beyond POSIX, and it would be impossible to do this in POSIX way. The second question was regarding per thread, I think, protection. This is not really feasible. So, I mean, it's still a single address space, and we actually cannot do this per thread. It's also not clear how this would help you. You could construct something where you have semi-shared address spaces or something, but basically it's the worst of both worlds. You pay the same price of having separated address space. It will basically be a separate address space identifiers if you do that, and the associated costs and CPU that you have with that if you were to do such a hybrid. And you, of course, have less protection than with actual processes. So it's simply not worth it doing that.
Great, thank you, Helga. So there's another question from a community member referring to previous slides saying, wait, performance is improving. That is counterintuitive. Don't know if either of you have anything to add. Yes.
Yeah, I think I explained it later on. Probably the question was before I talked about it, but I can repeat we expect currently we are seeing that some system calls are bottlenecked in the kernel, and that's due to the per process lock. And the hope is when we move Canister to different processes, we avoid that bottleneck.
Great. So hopefully that clarified the question for the person who asked this. But if not, definitely feel free to let us know in the chat. So next question, does process sandboxing method also protect against Spectre meltdown class of vulnerabilities? I read that's another concern for serverless where multi-tenant workloads are vulnerable.
So yes, will protect against Spectre. So the initial goal is basically, okay, it's a bit more complicated than that. So there's trivial kind of Spectre attacks against anything that is in the same process address space, and these attacks you basically squash by simply moving this into different processes. It is a lot more difficult to conduct cross-process Spectre attacks. It is possible. Or it is not impossible, but it requires a lot more effort. In particular, it also requires specific code gadgets usually that you need to do there. So there's also other aspects to the sandboxing protection that will make actually generating arbitrary code gadgets inside the process a lot more difficult. For example, by moving out the compiler into a separate process and protecting it sufficiently that you actually can't generate arbitrary code, but again, always subject for all code gadgets that you can produce to what the Wasm compiler is willing to produce, and that's going to be very difficult to produce suitable gadgets for that. And that's another part of the answer. Another part of the answer is that once we have process separation, we are of course also free to investigate into proper isolation scheduling, for example, ensuring that we never co-schedule security sensitive operations of the IC with, for example, Canister user code, isolating these onto particular cores, or doing also temporal isolation by ensuring that they are strictly sequenced with each other and do an interface. So for these, process separation is a prerequisite, but it's not necessarily the full story. But of course, Spectre and cross-process side channel attacks are in principle also on the thought horizon.
Great, thank you, Helga. And Ulan, do you have something to add to that?
Oh, no, I think Helga did explained really well. So maybe as a summary, within the same process is almost impossible to protect against Spectre and Meltdown, right? And with the process boundary, carrying out these attacks becomes maybe infeasible, or at least very difficult. So the process boundary is the right boundary there.
Great, thanks both. So next question from our very own Gabor. What about the Wasm stack? Where does that live currently and in the future?
So currently it lives in the replica process because that's where we execute the Wasm. And in the future, it will be moved together with the whole Wasm engine to the sandbox process.
Awesome, thank you, Ulan. So that brings us to the end of our questions today. So unless someone has further questions, any last minute questions, we can keep this short and sweet and close for today. So as a reminder to everyone, the vote is ongoing. So please log in to the NNS app to cast your vote. And big thanks to both Ulan and Helga for preparing this presentation and discussing the design and pros and cons and so on and so forth. And thank you to the community for attending as always and for your wonderful questions. I will see you all at a future community conversation. Bye, everyone. Take care.